Datsun. Well, you know, Charlie Datsun, the lawyer. You know, to correct
Okay.
it, we done this a little bit.
All new batteries.
I brought, they're sealed. We can take them out of the package, Frank. Now, I also brought a lockbox. Any batteries you want to let sit, we will put in the box.
We're gonna take the key.
And you take the key, so you know it's in. You know what I'm saying?
Yes.
I mean, it's only fair this way. I
Okay.
think we're fine that way.
So, I got all the
Now, do you
calibrated
need anything?
instruments.
You need cords,
I need
power strip?
I need 3.
Would you like me to grab some extensions out of my truck? I have a bunch. I borrowed one of those. Oh, no, the blue one's available.
No, I have a power strip here. I'm good.
Okay.
You don't have to.
Thanks, sir.
We're fine. Franco's got all the outlets he needs.
Well, I got an idea.
You didn't want the cage, did you, Frank?
No,
We do have it if you do want it, so.
no.
I just remember we kept bumping our heads last time.
Right. And
Okay, here's the power strip.
doesn't do any good.
And then I'm gonna plug this in for you. It should be fine. If you need additional, just yell at me.
Now, you want a clip lead onto things, right, Frank? Is that what you want to do?
Use clip leads.
Yes. I have a couple of leads
Okay,
here.
if you need more, we do have them for you. Okay, you're all set. If you need anything else, you just let me know. Make sure this is in. All you have to do is, I think you're on, so we should be pretty good. Frank's gonna take these out. John's putting them together. Do the primary one, then we'll do these. Lockbox, like I discussed. Anything that Frank wants to set, can set overnight. He takes the keys, he opens it the following day.
I'm just standing here watching, I don't know anything.
Well, just I want to let everybody know.
These are brand new. What's it, Gary,
Yeah.
what's the charge on these when they come out? They're flat?
Oh, I know nothing about it.
I don't know, I just,
John, what's the charge?
I mean, there must be.
Is there any, I think they,
Normally,
Ready to go, boys.
what are
these
they?
are lead
Here, Frank.
sets. So they.
I think there's-
I'll go to 0 and it's full.
in there.
So this is,
It's just adjustable supply, you're on amps,
yeah.
so they're just short. You can put your meter in. Give them a few minutes while we solder together, at least the primary.
All right.
Because it doesn't make any difference if those are flat.
They have a charge.
Yeah, it's just not all the way up.
It's just not all the way up, and that's the way we want these anyway.
So they're virgin batteries.
They're virgin
You're seeing
batteries.
them.
We found out something about this, Frank, that I have to state. If you pull this battery below 4 volts,
Yes.
it damages it.
Do we have specs on those?
We can,
Lowest.
well, the final,
Permissible voltage, and so normally it depends on the
well,
discharging process.
right.
The time of discharging, how low
Right.
you can go.
Well, what I noticed is I've got a whole bank of them over there, the ones that we brought down to 4 volts.
Yeah,
You can throw them out.
really?
Yeah, they won't.
Yeah. So, I was reading one of the specifications, it was saying if you rapidly discharge them, let's say in an hour, you can go down as low as 4.7. If you are discharging them gradually or with low current, then you can only go down as low as
6, right?
5.7 or so.
Yeah, I thought it was 6, but
But this is a particular lead acid
Yeah.
battery, so
it's
we
a
need
tough
to,
one to do it with.
we need to get some idea
Yeah, where you want to
These.
take them.
on what these are.
Well, okay, then I'll explain the machine, Frank, to you. What they are. Notice that as it's hooked up on its batteries right here, these are reverse connectors,
Yes. Ah, yes.
so that black is actually positive. If you make a mistake there, then the transistor, I'll have to go home one time. So I guess what I'll do is Frank needs to make connections.
We need to get writing on it.
I'll give you those. Tom. Okay, we're gonna solder these together, Frank.
Okay, fine.
I just think the cover's too busy or too.
We should check them because
It's kind of busy.
you never know.
Well, I don't know.
Okay. So you got your disclosure agreement. So here's one immediately.
Oh, thanks a lot, Frank. I
You're welcome.
appreciate that.
Coming.
Now you wanna mark these, Frank, you wanna call this 1,
Yeah.
2, and
Yes,
3,
please.
right?
Yes, please.
Frank, I'm gonna sit on you a lot because I've had a broken back. I don't stand very long. Not trying to be impolite.
Frank, you yell at me when you want a cup of hot tea, okay?
Yes. Okay.
Well, when you're sitting here, and you look at all the different places you're doing, you gotta look really good. No, that's fine. Right, but we don't have any KG, we could have something that would be in the field of electronics. When you go to a school, you'll see all kinds of things. This could be a variety of things. So Bob's gonna offer us 3 or 4, 5 or 6 different versions, either in square, ring, and he's got a book like this, and he says, he liked it right away. He says, "Hey, that's real simple. I can use it." It's just a logo. Not the name. No, it's not. Oh. We want to name it, doesn't have a definition, doesn't have a meaning.
I meant to bring Frank the cordless telephone that uses these.
Yes.
The warning light comes on at about 6 volts. It says recharge.
Nice.
So I can't tell you why it comes on at 6 volts. I don't have no idea. I don't think they would. See, batteries, you never know.
I heard.
Yeah, it comes on and clicks on the phone, it's gonna bring the phone back. Yeah, this is one secondary battery. You can analyze that. It's hot, so that's mark number 1. This one on market number 2, Frank.
Fine.
Is Don in Las Vegas? Where'd Don go?
He's, wasn't gonna make it today, I'm not sure what his schedule is. Frank, feel free to address the camera and tell us what you're finding there, because I'm not going to be able to get close-ups of your readouts and all that.
All right.
If you just want to narrate this process.
Yes.
And we'll give you copies of this again, Frank.
Fine.
Why don't you pull those headphones
Which wire was in?
out of that processor, Gary?
Yeah.
From the station, pull the headphones up.
Thank you.
Yeah, no, what you need to do is you need to move it into the escrow account.
Can't do anything about the lighting up there.
Express out of the escrow account. And then you can Walsh.
So that's battery number 2, Frank, coming up. I wonder if I should mark these. I think you can see.
Morning, Mark. Morning, Mark.
Glad you're here.
Yeah.
Where's,
Don's not making it today. One of this year. And I've got like 10 hours of tape. So we're gonna just roll them over. In fact, we're rolling right now. Tom, I need to step out of the camera. Sorry.
All right. They also have a fax machine. Okay. This is Tom's fax machine working. It's a fax machine.
They've got to be numbered or like.
When it, does the line come to this, it breaks or something, or does it go to the other?
I didn't look it up, I also suggested so that
Secondary number 2. So you can check that one.
Yeah, we're rolling now, so.
Okay. Frank. Hensel, that's it. You're right in the middle of the, you're in the middle of the,
Why, you guys doing it right now?
yeah.
Yeah, they started building. So.
Good morning.
Hi, Frank. Nice seeing you.
Seeing you again.
Do we have a red marking pen?
I know.
Secondary. It's hot on top. 2 secondary, right, you've already done that.
Yeah.
This is number 1. Secondary.
Honeycomb? Yeah, okay. Second.
primaries. Okay, now, what we have to do, Frank, is, I guess we'll have to clip lead everything.
So,
This is your primary side,
yes,
all right?
yes,
This is your secondary side.
yes. And which one are we going to use as a primary?
Same kind.
And do we
If
have
you-
a charged one?
Yeah,
Fully charged
right
one?
there. She's up.
Also,
Yeah, she won't take no more. I'll let it sit just a few minutes longer while you analyze it. Because you're gonna know what they're gonna do, right?
yeah,
Okay. So, I think I should go find another one of these connectors.
okay.
Or actually, no, you need a clip. Because you gotta have stuff in series, right?
Yes. So,
Okay. Let me get a piece of masking tape. I got all those clips
yes,
for you, but
thank you.
we're gonna have to take a meter and measure each one. They're from radios. Sometimes they work, and sometimes they don't. I'm gonna mark this foot. Then I'll put this on there.
When he gets the Nobel Prize.
Well, let's hope I'll be down, sir.
And this is
We'll
plus.
nominate him.
Okay? So I've got this all marked for you.
They're not because they don't have money.
Right, plus, minus. I'll give you some pieces of shrink tube,
Yes,
right?
okay.
Some big ones, so you can put the clips in, so they don't short together.
Okay.
All right, we'll do that in a minute. I'll mark all these for you. Okay, this is primary. This is secondary. That's kind of neat. I want one of those, Frank. I want one of these.
Yeah, these are power analyzers. So they typically, they can be used for analyzing even waveforms and for
Really?
harmonics. This is a normal.
This is plus sec, SEC. See, when you put these damn snap plugs on there, Frank,
Yeah.
right? You have to reverse them because you snap them on.
Yeah.
Yeah.
Yes.
Minus. See here. These are the original batteries that have been on the machine since the day the machine was built.
Okay.
Notice the difference in the battery.
Yes. These are.
They're 6 volts each at 1.2 amp hours.
Okay. So they have 450 milliamp.
No, these are 500.
Oh, these are 500.
That's all we could get, Frank. That's, yeah, that's 500.
Yes.
Let me tape these so that when you move them from bank to bank, right, they don't fall apart on you. You can see through that, right?
Yes.
You're gonna number them, right, Jack?
Their number.
That's our song right
Oh, sorry, Frank.
here. No problem.
Here, John goes back to the soldering bench.
Yeah. Faulty connector. Hard to solder. With such small terminals. And I'm so blind. Where'd the tape go? doing it, huh?
Yeah. Discharge. And we can have,
5 amps.
yeah. Oh, it started off with 15 amps. So we got quite powerful.
Yeah, you don't wanna do that one, we'll go wacko on you.
Let's check the voltage. 11.8.
What are you finding, Frank? There's just a little charge in those batteries?
Yeah, there's quite
Oh,
some
no.
charge.
Quite some charge.
Yes.
Yeah, no, here's one here, Frank. I'll show you what happens if you take them down below.
Yeah.
Here's one here that says you can't charge it, no matter what you do. So you might want to put that and just look real quick.
Okay.
What happens if you go below a certain level of it? Yeah. Those were the original ones you took down.
Yes,
Well,
I feel them.
they're dead forever. I like that little analyzer. That's the thing to have right there.
So it still has 12.8 watts.
Well, it says that, right?
Yeah.
I can't get it.
12.8 watts. That's what it's saying. Still getting 2.6, 2.5 amps still.
See, it won't take a, no matter what you do over there, it won't.
Maybe we need to discharge it properly.
Yeah, we're not gonna use it anyway. I just wanted you to see, so you know.
Over hours. So if it's discharged at a low rate,
Maybe
it
you
might
could say that, right?
regenerate itself.
Okay, I'll take it back, because we don't need it. You're gonna do these.
Yes. Okay.
Got hot, Frank.
Yes, sure. If you discharge it at a rapid with short circuit, yes.
Oh, that's why you're doing them in order, right?
Yeah, actually I'm measuring voltage and current at the same time.
What's it got, like resistor bank in there, calibrated? Wire loads, right?
Yeah, it's just a single phase power analyzer.
Oh,
So we
How
can
about it, Frank?
integrate, and then we can directly measure amp hours here. Or watt hours, whatever you want.
I know you and I ran this belt. And it ran that way the whole entire time. You know, it's almost like impossible to destroy these. It ran with that cracked belt. We put a new one on, take time. Okay. Yeah, so this is your primary. You need to have a diagram of this.
Do you have one of yours, the nice resistors? We can use maybe something like
I have what you did last time, which was this 8
the
ohms.
8 ohms. Okay,
Yeah.
let me measure it. Just with the calibrated instrument.
I have a precision one in a box, a 250 watt precision one.
That should do it.
I never trusted carbon. I'll go get you a wire one.
And 2 ohms, this is neither. Let's double check with the other one.
How about this, Frank, right here? 1%.
9.1.
Yeah.
8.2.
Yep, there you go. Closer, right?
Yep. Let's check it. Is that one here? 8.3. Is it shown? This is 9.2.
Yeah.
We just need to know the value. That's all.
Okay. Whatever one you want to use, this one can take all the heat. This one
Yeah.
got hot.
Yeah, okay.
I'm gonna tighten these probes up for you.
So we need a couple more pleats here. Secondary battery.
And we've begun to open up the brand new batteries. Would you like a Sharpie? Mark those?
Yeah, there's a pin right there. Okay, what we're gonna do is we're gonna solder these together, Frank.
Okay. Do we know about the stage?
Well, we're gonna solder them together, we're gonna test.
Okay.
We'll put them on the power amp.
Okay.
How you doing?
Good.
I think, Tom,
John, could you point me to the master volume for in here, so I can turn it down?
Oh, it's right here.
Oh, how convenient for you. Thank you very much. Good morning.
Tape is rolling. We're documenting
The process of building the initial batteries from the package. Okay, gentlemen, I'm going to go through a tape change.
Let's say, just stand there for a second and cut.
We need about 8 more minutes on this, Frank.
That's fine.
And it should be full enough to go.
Okay. So we have 8 volts.
tell you what I'm gonna do. My bad. Yeah, this one right here, yeah, the alpha.
Capacitor primary, right here.
Have the probe on the
What do you want measured from?
the waveform of the, or where you feel like to. So, yeah. And then,
You
of
want
course, yes, you need
waveform of the capacity.
to note the capacitor.
The motor?
Whatever goes to the battery, so we can have
Oh, okay, right here.
process.
We can put this right on the, we'll put this right on the positive terminal of
Okay,
the battery.
that's fine.
Okay, do you want to do all three at once?
All three batteries? No, just one.
You want to do all three?
Just one.
Can you do all three, Frank?
Probably.
Can you permit all three?
I don't see why we can't.
You can do all three. You can parallel all three of them.
It'd be very much to our advantage if you can allow all three to be charged.
Okay, let's do it.
And then,
check how much energy is on all
Yeah.
three.
Okay?
yeah, as soon as he gets down to this one time, we'll clip lead them together. So what we'll do then, Frank, is we'll take these pluses and put them together, right? And we'll make a series bank, or a parallel bank,
Parallel bank. Okay,
okay?
yes.
Want to do that?
Yep. That's discharge here.
Or we'll clip lead them together? We'll check the clip leads first.
Let's check those
Okay.
batteries.
Yeah, that's all.
Are they down?
Not yet. The problem is with down, is really if we rapidly discharge them, they
Yeah.
are not down. They keep probably something like 60% of the charge still. So we can not really say that they are down. That's one of the disadvantages of rapid discharging of lead acid batteries. That they,
I know when you do it in your car,
Okay.
it's down.
yeah,
I mean, the car won't start.
there are not enough amp hours left,
Yeah,
but
right.
there's still charge in there. So you could,
Okay, this
Have
is a primary.
okay,
Okay, and we'll call this 1A. All right,
yeah.
that's going to be our primary.
So in order really to determine down that discharge them over
Do you want to discharge them over it? Yeah.
the next year we can do it.
Sure.
Tomorrow morning we are going to do the same.
Okay.
Stuff out of your way here.
You want to get this cut for you. Oh, I see. You can put that right across the 8 ohm.
Yes. And I have around about 1.44 amps discharge. But, closely monitoring the voltage so
Yeah.
that we don't go below
Yeah, they say when the
4.7. That's the limit for rapid discharging typically.
yeah, well, right.
4.7 for
So
6
5,
volts.
right in there.
So we have 2, so we have 9.4 watts.
Okay.
That's our absolute limit.
On
Otherwise,
this
we
cell.
damage them.
Yes. So this one stays the way it is. We don't do anything
No,
with it.
no. No, we are going to hook it up to the power analyzer here,
Okay.
but
This one?
we are, yes, we are just measuring the voltage and then we are going to measure the current here,
Okay.
the 120 milliamps, you're saying?
Well, that's what my meter said. We're going to
Yeah.
find out.
Okay.
Okay, so you tell me what you want where.
Yeah. How are we going to connect it?
Yeah.
This is going to be across
The battery,
the battery, should
Yeah,
read
plus.
our voltage.
okay.
Let's double check so that, yes, that's
Yeah.
my volt portion, so it should read.
13.5. Right?
Right.
Okay, now, this
Now-
is going to be in series,
Yes,
so we want a minus
right,
to the minus,
yes.
right?
And then this
Well, I'm gonna do it this way, because I know what's gonna happen.
from
Can't do it that way.
here, then
To plus, right?
to the plus portion.
Yeah, go ahead. Well, I'm gonna put this in there so we can't short.
Okay,
Minus,
yes. And that should go to the plus. And there should be no reading. Oops.
yeah, yeah.
There should be no reading as long as the motor is
Sitting there stationary.
sitting there, yes. This is the range sheet.
Be doing a really, yeah.
Do you have any stopwatch?
Yes, I have a clock. Will you give me a clock?
Stopwatch?
I have I got a
Okay,
clock.
Thank you.
Use mine as well.
No, that clock don't work. That clock counts down, Frank, so we'll have to use this
Yeah,
clock.
I
I've got
I
a
have-
regular stopwatch here.
Okay?
I could use mine, thank you. All right, so there should be no current flow at all. Let's see. Let's use a little bit more sensitive instrument just to check what current is. So 200 microamp.
Yeah. You know what, you want that in series?
I'm just taking this out of the loop for now. And
Yeah, right there. Yeah, pull back the other way. There you go. So you can put that probe right in there. That's where you want it?
Yes.
Go ahead, I'll hold it.
Fine. Let's see if there's any current. No, nothing there around. Oh, to amp.
John?
Okay, there's the clock.
The press release.
No current, huh, Frank?
Well, that's exactly.
No leakage current.
So we are on scale 200 microamps
Yeah.
and we don't read anything of course. Okay.
So now we put the green back there, right?
Yes, please. And
Will
this
read.
meter should read. So why?
It's sitting, because we charge with a flat meter.
I see. Okay, that makes sense.
Yeah, we have no current leakage, so it's just,
So as long as it sits like that,
we can't waste it, right?
we are.
And you're gonna go,
You are switching
this
to
way,
it's
okay.
across the PN
See?
junction, yes.
see,
Okay, yes.
okay?
We have our
Yeah,
100,
yeah,
100
it'll-
something milliamp.
So you know what it reads.
Yeah.
It will read once you fire it and start it.
So the only leakage current should be across the PN junction.
Yeah, right.
And this
Yeah,
is,
sure.
what, mega ohms somewhere. Yeah.
Well, I know they've been sitting on those things for years, right? They don't leak. The batteries die and leak before they ever. Are we down?
No, it's 10 volts still. So we said 9.4 is our absolute
Yeah.
lowest limit. 10.
Little stronger battery, huh, Fritz?
No, it's gonna get warm.
Really?
Yeah,
That's a 250 watt resistor.
gets warm. These little batteries. Yeah. So we are at 1.25 amps still.
But you might catch it.
Yes. We are discharging battery number 3.
So what we would like to do then is put them all in parallel,
Yeah.
charge them all.
Yes.
He's got the treatment. The treatment is
Then
removal of proteins, right?
maybe some photos of the waveform
Yeah.
and so on.
To deactivate.
Well, you know, the batteries that usually run on it, Frank,
Right.
are these here. And they're 1.2 amp hours.
Yeah.
So you're gonna just exceed this just by a little bit.
Yeah. Okay, 9.5, 9.5. So let's stop at 9.5.
That's how you.
Okay.
9.5.
We're stopping at 9.5 ton. Fine?
They're not hot.
No.
So this is number 3. Let's check number 2 again. So we are at 11.8 volts.
This one's
Charge
ready to
current
go.
is 145 amps again.
And a lot less disabling. Use your wiper for having anything. Do they split 50 days after? Yeah, they got early.
So we are going to put the current loop again.
Yeah, we're gonna connect
The
this.
meter,
Yeah.
the current pass of this meter in between, because this guy doesn't, this guy measures any waveform. So
Okay.
even these odd ones, and we can even analyze the wave.
As long as it doesn't pull load, right?
No, it's going to be in
Series?
in series, yes.
Okay.
So the current pass of that one is going to be in series with the charging.
Okay.
11.14, we are still on number 2. So this one is ready.
Yeah, I got the lead from the one that's ready.
Okay,
Yeah.
13.45 watts.
Well, that's good. They usually flatten off at 12.50.
Yeah, so we have, what, 20%? Normally, you can get more. 14.4. But then, of course,
They go,
yeah, after you disconnect the charger, you go down to typically 10%, 110%. So we are still at 10.9 volts here, and the discharge current is still 1.35 amps.
you have to wait.
Just a little bit.
Yeah.
We are just dissipating some, converting some heat here.
And so this will go over here. The next one you put in line.
Yes. I'm going to give you this one here, number 2, in probably 3 minutes.
I just hope these are all good.
You can measure them.
Yeah, you know, carefully.
Yes.
Make it deep for
Okay, let's make it deep.
Good, bring your meter over here. Measure these two, measure the black and the green. Okay,
This is fine.
we know this is good.
This is fine. So let me watch the voltage here.
Good. So this is your next battery, red and black.
Okay.
Okay.
It's not shorted. It's still at 10.48 volts.
Okay, check these. You checked these already. Primary. Yeah.
Primary has roughly 17.45 watts, and we are going to put in parallel secondary
3 batteries, right?
1 through 3, which are discharged to 9.5 volts. Okay.
You're not there, Frank.
Roughly 10.
You're not.
Yeah.
Yeah, you really don't want to go down any faster, do you? You're at
No.
9.9
No.
now, 9.5.
We are anticipating 12 watts.
Right.
9.8.
Dropping that.
7. Yeah. It goes rapidly now. 7.96.
These are the
9.8, 5.4, 5.3, 5.1, 5.0.
okay.
Okay.
And this
It's
one
not
will
hot.
go in parallel.
So now we need to just discharge again, number 1.
So the yellow becomes plus on this one. Okay.
Yes. So we are 10.8 volts.
Maybe
We
wait.
have previously discharged already number 1, so it should be down pretty soon. 10.75 volts. So we have 1, 3, and all of them are new batteries, yeah?
Yeah. Brand new. You'll be there a while, Frank. Yes. You don't want to take them below, right?
No. 10.1.
Tom, should I get you a higher chair?
No, fine. What, you got a Harold?
Yeah, they sit you at the table.
Huh?
Sit you right at the table.
No, I want to sit back over here out of the way. Y'all are doing fine.
Green is ground.
Number. This is minus, yes.
What?
So we have them all in parallel.
They're all in parallel.
Let me double check. 2, -2, minus, to plus, to plus, plus to plus, and then we have here our.
Right, this will be minus, this will be
Yeah.
plus.
Okay.
So you wanna go, do you wanna put your
Yes,
series?
yes, please.
Here.
Not the resistor, but just this guy. So we are going to
Here's
check
plus.
let's connect the voltage loop first, which is this one. Oops, so let me get that out of our way. So we are going to connect the voltage.
Right here. Here's plus.
Yeah. Should we? Or we can connect the voltage loop to the batteries here. Yeah.
Okay.
And now we are going from plus
Right,
to
here, to the battery plus.
battery plus. Yes.
Just clip it on here.
Sure.
Okay.
Okay, so we have 12.12 volts. in
That's
parallel.
typical for a lead acid to do after it's been
Yes.
drained, right?
Yes.
So now you wanna go?
Yes.
You wanna
Let
start?
me
Okay.
let me start my stopwatch here,
Got a second timer?
and yeah, if you
Okay?
can run it. Yes.
Timer goes.
I don't think this thing is got enough raw here. We see eye range,
It's at the lowest, so
you wanna be,
it's 20 amps. That's the lowest. It's 400, 200.
it doesn't wanna run it.
Okay, so what is that current
So let's
loop?
find out.
Maybe
Let's find out real quick.
this is our
Okay,
current loop, not.
that should run.
So 200 milliamps.
Oh, you don't wanna run.
Okay, let's double check. Maybe this one is too high.
Let's find out. Plus. Let's just try this real quick. We're minus here, right? Plus here. See?
So without the instrument it works.
Oh, yeah.
So this is too high
Too much.
resistance.
Okay, I'll go get another meter.
Okay,
And you can calibrate it. You can use that one, right
I
there.
can use that one
Yeah.
at highest. What I
And
left.
you use this for the voltage and that for the current,
Okay,
right?
let's use
That's what
this
you want to
guy
do.
here
Okay, so here,
at highest DC
well, you
current.
will be on like 500 mil scale.
Okay, 200. I
200 should be all right.
200.
Okay,
Let's use the 200.
let's try.
That should be fine enough, hopefully. Otherwise,
Okay, all right, so here's your plus.
okay. So we are
This
coming
is
from
coming
the
from the
battery.
battery. We need one more clip, Frank.
Okay. Might not work because it might be still too much resistance. Yes.
It is. I'll go get you a meter that will.
Okay, let's use the 10 amp scale.
Okay, go
That
ahead.
should work.
Yeah. Okay, there you go.
I just started my timer with the 10 amp scale.
Okay. Good. That's low enough.
Building the chart.
Fine. What is our...
Okay, now you want that on the,
Yes, please.
you want this on this waveform output to the battery, right?
Yes, please.
Okay. There it is.
Okay. So let's figure out this guy. Scope. Trigger, auto trigger. And then our range.
It's rocking, isn't it, Frank?
So it should be on volts. To find it.
top.
Yeah. Let's put it on the cap, Frank. Across the cap, see if the cap's dumping.
Okay, yes.
Because if there's no load through here,
Yes.
it won't dump. Because it's gonna drop in voltage. We should see the cap charge and discharge. You go.
It's round about 1 second.
Yeah.
We have
T10, right? Is that where you want it?
It's 100 to 1, so
Oh, it's 100 to 1.
yes.
I hear it pop, so it must be working through there. I see no amperage at all, but I see the battery going up.
No, that's okay.
Yeah.
Amperage is right. Voltage is energy for amperage collection.
I do see it rising here, Frank, you're right.
Yeah.
Gentlemen, I need to change tapes.
Okay.
Okay?
Yep. Yeah.
Yes.
Rocks it up there, huh?
Doesn't know where to trigger.
Oh, go in further with the time, decrease the time. So you start to see the wave, the sawtooth should be.
Doesn't trigger.
That's water.
Okay.
Let me get you the tacky scope. Actually, the tacky will trigger on that.
Okay.
Or trigger on, but remember I made that problem?
Yes.
Here, this is good. I fixed it. Let me get you the tacky scope. I'll just parallel you.
Okay. Okay.
So,
will try from this side.
Move the stopwatch. There we go, stop.
There you go, Frank. There's your way.
So you have a. What's
I got it same place you have it.
And what, 10 to 1, the probe?
I think it's time for one. You set the times in here.
What's the probe itself?
You set the probe inside. Menu. Probe type 10. Okay? It's set on times 10. See? Okay.
All right.
So just clear this menu. I don't want to clear this whole thing here. Now I can span this out if you want to see what it's doing, right? All in butt, huh? It's moving. Frank, did you want this on DC or AC?
Really doesn't matter. No,
Did you get away?
no, I cannot select the 100 to 1 probes, only the 10 to 1.
But you can see it here, right?
Yes.
See what I'm doing. Raise it up. We actually have another set of probes for this that will monitor the voltage for you too.
Okay. This is the...
What is this, the key?
Yeah, it's at the capacitor, so you should see it. It's clicking away, Frank.
Yeah, but I can, for some reason, not select my 100 to 1 probes.
Well, you have this one, it's right on beam. We use that all the time, right? That's the best little thing. In fact, it's got a voltage monitor meter in it too. Right, Frank was looking for the book, see? Remember we were looking for the book, you couldn't find the damn book?
Yes. Got my book here. But you are telling me not to select the 100 to 1 probe.
This thing is capable, Frank, of doing steps for you. I'll show you.
Hi, who is speaking? Kelly? Hi, good morning, Kelly. Okay, thank you. How are you doing? Can you connect me with Colorado, please? Yes. Thank you. Hello. Hi, Colorado. Oh, so far so good. Except that I cannot select on the fluke scope meter the 100 to 1 probe. Yes. Input A. Again, let me just see what happens here. Let me switch it off. On. So now I go input A. Yes. Does it? Does it say select? I probably have a different screen now here. Okay. No, I think I am in the selection mode here for somehow
Good.
I have strange screen. So how can I reset it?
Look at, see it jump up here?
Yeah. That's good. Auto set. Okay.
This is
Okay. But my probe is now 1-to-1.
Well, you got about 4 hours to go.
that's good.
No.
Running it in resonance between 1.3 and 30 million.
No, it doesn't. Just
Each way.
try to.
That's the way. You see this? No. This
I was
way.
looking at one vehicle, though.
No.
Good
what's
question.
doing-
I changed
that.
everything changed here.
What's
I
actually
was
doing
trying
it
to
faster.
get into this
What's exactly
F5
capacity.
select mode, and it's still in there. So what do I have to do?
We can look at the battery meters.
That's good.
Show you what we see on the battery.
Yes, but it. Input A.
This is on the battery.
Yeah, that's good.
Yes. Yeah. F1 is called meter ohms, and the diode means external milliwatts. That's what it is. Okay. No, it doesn't. No. Only, no. Let's see. Touch hold. No, it's auto.
Look at the battery.
It's not on hold. User options. Probe menu. Oh, I have to put it on user options. I see. And then I have right inside the probe. Okay. So, but it only gives me a selection of 10-to-1 or 1-to-1. Okay, scrolling down means, which one?
So what is it, John?
Oh,
That's the waveform on the battery.
no. Screwed it up again. Okay, let's do it again. Probe on input A, 10-to-1. And no, it doesn't allow me. Doesn't have any
You got it
option.
now.
It doesn't have 100-to-1. It just has 10-to-1.
Oh, it goes into a dot. Yeah.
Yes, select item.
Yeah, you remember, we're charging 3 to 1.
Yes. Ah, okay. Then I can. Now I can. Okay. I see. Now I'm on 100-to-1. Yes. Good. Select item. Okay. And close it. Okay. Fine. Concerning the, it still reads input external probe 1-to-1 in a little window here. No, input external and then probe 1-to-1. Okay. So how can you select the input? Anytime I press input A, there's no change. Here it is. No, it's in a kind of strange mode. Frozen in time.
Discharging.
Yes. Yes, it,
So as soon as-
no,
as soon
then
as
it
the
would
iron starts
say
to
touch
get
hold,
correct,
no, it's on
the voltage still
auto.
builds up. You got to get that number.
Yes,
You
The main
get
thing
that.
is that voltage
on the left,
much higher than they normally have.
Yeah.
yes.
So we get extra energy
They'll move.
to do
It
more starting.
just has big readings there and
That's why they take that charge.
doesn't give any signal. The readings are not changing.
You have to have that
So
delay.
I don't know what's wrong here.
What's on, sitting on the back.
Input A.
What you see in that other stuff is that other,
Battery free.
well, the smaller ions and all the different kinds of currents.
That's a
in
good
that,
question.
They
I'm
are much lighter than the bigger.
Probably in,
That's right.
in scope.
With what
Yes.
it's changing.
Okay, now I'm, okay, I have your
I'm
red
only a model
input
builder,
A
I
and
know that.
gray input B and C are being used as inputs now. Okay, I have the wrong input selection as well.
Keep you that.
So I'm using
Here, Joe.
the B and C, but it is showing me the input as
That is not that.
the banana
Hal,
blocks.
Hal doesn't have this.
So how can I change the
I don't have
input?
that way before.
Well, he doesn't have this at all. He hasn't got this right here.
Yes.
He'll never get that.
So he doesn't understand where it comes from. Or how it comes.
We did.
Yes, but
Kind
no,
of makes you feel
it's,
good about
it's again,
that it's there.
but the input is
Yeah.
on the banana, on the red
4.27,
input
man,
B
it's
and
climbing.
gray
Feel
input
that?
E, B and C checks are being used as input now.
It's climbing.
That's what it's saying.
And when you go to throw that switch, you want bigger pump.
Yes,
You bigger pump.
so now I'm
Push it.
switching to
Let the motor
input
push
A.
first.
Okay,
Gets into resonance. Tom, you
display
see
input
people-
A,
Fans the load.
but I don't get it.
That's popping in there.
Coupling of A is these, doesn't matter. Trigger source input A, switch detect, no, that's all. Scope, yeah. Input A. Okay, let me read the book. I think I just need to select the proper input now. Okay, thank you, Gerardo. Yes. Okay. Fine. Thank you. Thanks. Bye-bye.
scale?
Yes.
Perfect. If you'd like to rotate that towards me, I can get a shot of the face of your meter. If there's something you don't know.
Might not come out to be.
Yeah, you can see it. It's dim, but you can sure see the spikes.
Right. Did you see what it shows on the battery? The tech is so low.
Yes. Yes.
Now the tech is showing you what's across the battery.
The.
Yeah.
This is across the battery. Yeah,
Yeah.
we're on a capacitor, but I'm
Yes.
across
Mhm.
the battery side.
Yeah.
And that's what the
That's
battery.
what we saw last time as well. So, how can we analyze this?
I leave that to you, Frank.
We could analyze it with this guy.
Did you get this to go?
Yes.
Oh, okay, good.
So it reads this sawtooth.
Same as me. Yeah.
I had a problem in selecting the probes.
Yeah, and then this is what's showing up on the battery, see?
So this is in.
Yeah, because you're across the battery, you're looking at what?
Seconds, yeah.
Yeah.
Milliwatts per division. Get that a little bit more down.
Yeah, just go down here.
Oh, yes. Okay. 200 milliwatts. That's our 1 second past the
Yeah.
division.
Yeah, if you time that out, you know, it goes 1001, 1002.
Problem with the contacts here.
Oh, no,
No.
who's doing it? I mean, you could put force on it, but you won't see much difference. Eh? Yes.
Just the way.
You can see in the reflection of the brass going around the spark.
And
And you
that's
can
showing
see,
up here.
yeah, you can see your battery. What, do you have a DC scale? Can you put that-
Probably.
Can you put that on DC instead of AC?
I think it is in easy.
Well, we want to go to DC, and you want to watch the cap charging and
Yeah.
discharge. You know, you'll get the voltage between the two. Then you'll know what's going to the battery.
Let's get it a little bit more.
See? You climb up.
Yeah.
It takes them a minute to move.
Probably on item on DC.
Are you? Well, you should see the cap going
Yes.
up and down.
Yes, DC.
You should be able to see the cap move though. Here, the techie is measuring, see the battery voltage is right now is 12.5, see? Okay, now what? I'll move the techie over to the capacitor, all right?
So you
Because
have-
ground stays ground.
Yeah.
So we'll move this over to the capacitor.
You have a 10-to-1 call?
Yeah.
Gentlemen, I'm changing tapes again.
Now see your voltage on the battery?
Tape change.
See it going up and kind of unusual, isn't it?
Yes. Maybe I can have the probe.
Where would you like it?
Across the liquid.
Okay.
To show the pulse.
You know? You mean like this, the techie's doing?
Yes.
Then you just move this over here.
Try to analyze
be able to get it now. Now you're across the battery. Ground stays ground. It's, I'm gonna give you a diagram of the system.
Mm-hmm.
I'll do that real quick.
Yeah. I think I have one.
Well, no,
No?
I'll show you what it is.
Is there any reason why that is on the side that you can use for, I don't, it's not that much of a way, it's just, no, it's all right, don't bother moving it out, Frank, because we got all this food here, I was just questioning that, I didn't know, let's leave it alone, don't worry about it. I didn't know if I was supposed to be using it or what. Is it usable? Okay. Okay. Problem.
This is what you have, Frank. You have, I think you and I tried this one.
Yes, one more.
Here's what you have. These are all in phase. Every one of these, they all stay in phase.
Yes.
Primary system is isolated from the secondary system.
Yes.
Recovery of the back EMF from the motor,
Mhm.
right,
Yes.
is rectified, stored, switched back to the secondary battery. In 1 second, I thought this was 500 US.
Yeah.
Yeah.
Thank you.
Minus, plus. No, wait a minute, I goofed it. Sorry, let's don't go here. This line goes here. Floating isolation from primary to secondary.
Yes.
Okay.
Then
Yeah. Pass.
yeah.
Yep.
Yes.
1.14 times. And you can see it go up, right?
Yes.
Now you take that up higher by moving the switch. . 1 See, you don't have the same charge.
Moving?
Yeah, when you move this switch, right,
Oh,
you
yeah.
make the charge potential higher, which the scope can't catch. So you go down to this capacitor, which is 500 under normal charge.
Yeah, and the other one is?
The other one is 150 mics.
Okay.
So it's just a switch,
Mhm.
all right? So if you look at it, it's just a switch between the two caps.
Yes.
We never use the lower cap.
Mhm.
We never have.
Okay.
It's the 500 that works the best. It's optimized for the system,
Okay.
all right?
Fine.
So we have the 500 times the total voltage, which is about 40, 45.
Yes.
That's about, well, you know what I found really interesting, so you and I don't have to work at this, do we? We got everything at our fingertips here. Right. No, I mean, why not make it easy, right? Yes.
Actually, that's fine, just
Perfect. So. Yeah. Fantasy, 500. Energy voltage. Right. Yeah, we can move to the different things and solve this. Okay, that's your watt second.
But this would be, okay, 500 micro. Instead of 500
You want to charge storage.
You wanna take that out?
20. So you're getting a charge of 225 milliamps.
22.5 millicoulomb
Okay, now how do we convert that
into, that's the
into
charge.
watts?
You have to calculate then the energy.
Okay. And we can
So I guess you,
paste this,
yes,
or copy, right,
yes.
and return.
And then energy stored.
Paste that
So
in
actually,
here,
we
right?
can, no,
No.
we can measure it, calculate it directly.
Okay, okay.
0.0,
Excuse me.
0.0005 times 45 should give us our energy. So it's 0.5 watt seconds. 0.5 watt seconds.
So that's almost 500 mil.
That's 500 milliwatts.
Yeah.
Makes sense?
Yeah.
Really?
500 milliwatts
And what?
is all that's charged in the battery.
That's about right.
Yeah.
So the, yeah, capacitance times the,
And now we can tell what the power is if we take this, right?
yes, we have E squared times,
Yeah. CE squared, right?
yes,
Over 2.
okay.
So now we
So
can convert this to power.
Yes,
So we need to copy this one, right? We need to copy this one.
seconds.
Yeah.
In order to get our
Let's see if they got it here.
divide by the time.
Okay.
What time would we,
Hmm.
what time would we use?
Well, we gotta get that from your scope. We can get energy stored.
That measurement will give you the power you have to supply to get the batteries to charge. There's an additional energy input inside the battery
Okay.
that will not show in that measurement, but it will show when you discharge the battery in the load. You know, it'll either be there or it won't.
Yeah.
So that'll be very rigorous. That's good.
So we're right. I'm right on.
Let me think about it.
Okay, you're doing it, Frank. I'm just showing you the computer's there for you.
Thank you. Good. All right. Our time, we have 48 minutes.
Do we run until we die?
Yes, please.
Okay. We'll have lunch.
Lunch already?
Well, no, but
It's 10:45.
So we're gonna go until the primary is completely discharged?
discharge until the motor stops.
Very good.
Two isolated systems. And we're like doing what, Frank? 3 to 1.
Yeah.
It'll depend on what you discharge it from the battery in a load test.
Yeah.
That's what it credits with, what you actually are able to get out of that.
Yeah.
But that's good. That's still
Okay, so let me make some notes here.
I like the way you work, Frank.
So,
You've done this a while.
excuse me?
You've done this a while.
Yeah, yes. Testing is, I usually have a technician with me
Yeah.
who does all this stuff.
I was starting to say, usually you probably have an assistant doing all that for you.
I have 4 engineers working for me, 1 technician, 1 assistant, and
Very good.
an
That's
inspector for
Well, we're
production.
glad to see you. All these boys need is just a good, straight, honest test, that's all. No problem.
So we have battery 1, 2, 3,
Yeah, motor goes into revenue.
A little bit of that may be, well, of course, it could be genuine, there's parts of the circuit. But that tabletop has a mechanical vibration also, which is
Really?
feedback from part to part in the system. So you can be doing quality feedback by mechanical resonance, mechanical feedback.
Yeah.
You can put your hand right on the corner of the table, there close to this corner, you can feel that, that vibration.
So dyno, we don't have a dyno to handle the
Right.
mechanical load. I only have mechanical brakes, which we use for overload tests for motors, so
You can break it.
I know, but in order to determine the mechanical.
Okay, you need a string with a scale.
Yes, string with a scale or no, a normal measurements direct?
We tried to get one for you,
Yeah.
Frank. We tried everywhere. If you want to
They
run
got
that,
big ones for
if
cars.
you want to run that 454 out there, Frank, they got a dynamometer for it. So how do we calculate it?
I don't think you have to worry.
No.
Let me show you something on energy balance.
Yes.
And as I say, the measurement truly does that. It doesn't, we're not saying that. We live by the measurements. But the process we're using has an extra energy input, or obviously we were in business, you see. So it's really an open system, receiving a little bit of extra energy in it. And the point is, can we catch enough and use
Yes.
enough of this extra energy? If we don't, we just have an ordinary system.
Right.
So when you go through all of this, we have primary power supply. This is what we have to pay for right here.
Right.
Okay, we get a motor generating unit that's turning, it's doing some work here which I'm calling C. We don't know what that is, but that's the label for it. The motor has internal losses which we cannot take credit for. That's okay, but we list them as energy balance. There's energy going out right here, we're losing.
Yes.
We call all that B. And we have this input that, we claim we have
Yes.
that we can't see. But,
Right.
we say we have one, we tend to violate no conservation of energy law, never.
It's going
Okay,
up
we
higher.
go to the three secondaries. We're putting so much energy, but there's a charging efficiency.
Yes.
No, it's not 100% efficient.
No.
It loses some. So we have these little losses from each battery that we're going to call F, F1, F2, F3.
Yes.
And what we're calling D1, D2, D3 is when you take the battery off after charge
Yes.
and you discharge that in a load, this is the useful work out.
Right.
It's not whatever you put in the battery, it's what you actually can claim you managed to catch in your
Yeah.
It's a rigorous workout from the system when you do it. So then the operator input becomes A. But the total input is A plus E. It's not just A. If it's not, we have nothing but an ordinary system.
Right.
Yeah.
So the total output plus losses, you just add up everything. B plus C plus this D here plus the F that got lost in there. That's just where all the energy went.
Yes.
And we know that the only useful work out we got is C and D after you do that test. We have no other useful work out of it.
Right.
So we're not going to measure C because we couldn't get the dynamometer.
Yes.
So I wrote the equation here. The actual COP is defined as the useful work out, only what you get out, which is C and D. That's it.
Right.
Divided by what you have to put in. Now, normally we would have to put in more if something else wasn't put in.
Yes.
So this is the whole purpose right here. Since we don't measure C, we know C plus D is bigger than D. So we write it, instead of equals, we write greater than.
Yes.
So whatever that COP is greater than D over A, since C was greater than 0.
Yeah.
And that's just said if we sum everything up, we always have an energy balance. If we look at the efficiency, which is total energy input, we're always less than 100%, as long as we have a loss here, and a loss here.
Right.
So we're not violating any conservation of energy law. The whole point is, we either are getting an extra energy input here, which we can actually measure.
Yes.
We can't measure it, we can't claim we're getting this. It's just that simple.
Okay.
So, and we're willing to live with it,
Yeah.
even though we give this up, because that becomes, instead of equal, that becomes a little greater. If this number goes over 1.0, we're down home. If it doesn't, all we can say is we had a little more, but we don't know how much.
Yes.
It's really that simple. And that's okay, we're willing to live with it. I personally think, from having seen this thing work before, all the measurements John did, I think that with the 3 batteries, we can go to unity, even though we don't account for that. But that's okay, we're willing to live with it.
Well, because it's a
That's a-
secondary system.
That's a perfectly valid test, no problem. Good test procedure.
Fine.
That's the reason I say, I like the way you think.
Well, Frank's trying to figure it out too.
Well,
Yeah,
well,
because-
I can explain, by the way, eloquently, how we get this. And that is a little peculiar. Obviously, it's not in the normal textbook. But we've worked on this for some years, so we can explain that, and we can go over in physics and show
Yes.
it just never got into electrical engineering, but it's over in physics.
Yes, I read your
Yeah,
articles on this
so,
one.
see, we're not claiming that we have a new physics.
Yeah.
We're claiming we have discovered that there's a part of it that never got into electrical engineering, and we found out how to use that. That's all
Yes.
we did.
The same is true for the universe.
Exactly. If you had a windmill and you couldn't get a wind, you could never get anything out except what you cranked in. And neither can we. If we can't get a little free extra energy input, we have an ordinary system. Nothing of any to get excited about at all. But that's good. This is a straightforward, absolutely rigorous test.
So how would we get this little extra in?
If we had a small dynamometer, I found hints that in Germany they make them for people that do model trains and model little bitty model engines.
For the little remote control models?
Yes.
Yeah, something.
I think that's the only thing. I searched that internet for about 5 hours, 4 or 5 hours off and on. And that was all I could find. I found references to a couple of German places that apparently make little dynamometers
Yes.
for that, for size model motors,
Yes.
which of course is what we have. But I couldn't find any in this country. We can find them from cars and big stuff, but I couldn't find anything small.
Okay, I have an opportunity next month to at least check to see if something like that is available.
That's where it'll be. It'll be for the guys that do those precision models a lot, and little robot stuff, little robot motors. They're using a lot of those little robot motors apparently. So I don't know what for, but you know they have to have a little dynamometer to measure the little motor. But that's the only place I could find that people were talking about a dynamometer small enough to go, or something like. You know, the other things are huge things and very expensive. But this is good. I like this. But the main point, you know, we have to tell lots of engineers, look, we absolutely comply with the conservation of energy. We're not going to break that. You don't get a little extra energy input from someplace, you can forget it. You're spinning your wheels. You must have one. Eventually, you must be able to account for what it is. You must show somebody that, yes, that does exist. So if you don't doing that, it's impossible. Even if you account for the refrigeration burden, even a superconductive system is not refrigerated. And the efficiency, which is where does all the energy go? Do you get all of that out? No. No system you ever build will be perfect. So you're going to lose some of it no matter what you do. You have to have enough free extra input to overcome that. So we try to approach it, you know, quite rigorously that way. But this test will discriminate. See, we don't set up, of course we have expectations what we'd like to see, but it's the test on the bench that says yes or no, not what we like.
Sure. And if we cannot find what we are looking for,
Then we have to have something else.
we need to
That's
determine
right.
whether we have to use a different type of.
That's right. For example, if we didn't get enough in here to go over COP1, let's take the worst result we can come up with that we can think of. Then we're facing the fact that we've got to do something about that dynamometer.
Yeah.
Because right now, we can't tell you how much is going out there.
Right.
But that's okay. I think, my personal opinion is that we're not losing too much in the actual charging process. We don't have too much loss and inefficiency there. We can make it with 3 batteries. But still, it's the test that must tell us, not our expectations.
Yes. So I like to measure
It's a neat little rig for a test rig. It's good enough for a proof of principle.
So we can really hear that thing.
Yeah. That table, you know, like a guitar player. Guitar, you know, the sound of so it's chewing right on. Yeah.
By the way, Radio Shack said those batteries need to be charged for 18 hours.
Well, that's regular charge, though.
Yeah.
That's without the internal process.
Well, no, they said the ones you take out of the package, you should charge them for 18 hours.
Well, this will sit there.
They'll run.
Doesn't bother us. I think this will work okay. I allowed for that by looking at the inefficiency of charging the battery. If that's not too great, we're okay. If that is too great, then we're not okay. But we'll know when we get through with the measurements. I like that one instrument, that power, what do you call it, power data device?
Power analyzer, I said.
Power analyzer, yes, that's right.
So
I think I
let me use
would
it.
recommend to our guys, we'll try to get one.
Let me use it in the integrating mode.
What, if I might ask you, Frank, what do those cost?
I think the single phase are just around 2,000, two and a half.
Okay, that's down with something we can.
Yes.
Hope to get.
And are different manufacturers. We use them for typical AC evaluation. And we also use them partly for harmonics evaluation.
Yes. That's good.
But I think they are not going up high enough. In order to analyze the harmonics, you need to have a higher bandwidth.
Yeah.
And there are better ones available.
Yeah.
Well, most motors, Frank, are the ones you lay on the bench, okay?
Yes. So there are requirements, for instance, in Europe concerning the maximum amount of harmonics that can output, especially on those switch mode power supplies.
Oh, yeah, understand, this is just a lab, very proof of principle thing. But if you're going to commercialization or something, you have a very exhaustive series of tests that you have to meet standards. You can't just put a system out there on the market and say, oh boy, who could ding it? That doesn't work. You have to meet all kind of test standards for radiation, harmonic radiation, everything. You don't. You can't sell it.
Emissions, immunity, safety.
Yes. You can't put it out if it's unsafe. You can't put it out if it's going to irradiate people too strongly and cause health problems. You've got to have a safe product. So you have to go through a pretty exhaustive test series for that.
Yes.
That's what we were talking last night about cell phones.
What we do, yes. Let me try to put that here on integrating.
They really sneak those cell phones through.
Okay, gentlemen, I'm gonna change tapes.
Okay.
Okay, we're rolling again. Has anything changed?
No, no changes.
Very good.
Want me to make a fresh pot of coffee? Yeah, fresh coffee, I can make a black
I'll
coffee.
take a cup if you do, Tom, yeah. Frank's not a coffee man, though.
Nah,
No.
we'll keep him supplied with tea.
Can we make you some tea or something, Frank?
Oh, yes, would be nice. Can get some hot water. So.
space?
The regular. That's a decontaminate.
A lot of people think research is glamorous, research is slow.
Trying to isolate that squeaking sound in here, is that the bell?
Probably is. But I don't think that'll bother the bell and break. Shouldn't, those are usually awfully tough.
Yeah, it's certainly not like waxing your car where an hour and a half you can see the results.
No, it's slow. And you see all of the stuff that goes into it. You see a little more sitting on the bench. You see all the research that went into getting that report. Just like that, so exactly like it's built. Of course, that doesn't show. So,
Yeah, my first son was building it, so I'm fired up about it.
Sugar or anything, Frank?
Yes, please.
No sugar?
A lot of torque, and then I grabbed onto one of the
yeah.
doors and tried to stop it myself.
Well, it's all there and it's available to be captured and used, but it's like anything else, you know, the first automobile was ever built was a rinky-dinky thing and nobody thought it would ever replace the horse. I mean, that was a terrible contraption. But, you know, the next one did better. Eventually Ford built the Model T. And really it was the Model T that began to see that we had something that was going to get around. But it only faded away as a rinky-dink toy. But you gotta start somewhere. You don't start with all that.
You doing it right?
All the knowledge you need to build a Mercedes.
No.
Thank you.
Huh?
You're doing good on that first little rinky-dink.
Show me anything.
No.
Yeah, like you said earlier, for the theory of it.
That's right. And you see, the important thing is that original set of experiments.
It's not loading it while it's doing it, is it?
You may not have the best theory, you may not have confidence, but if it enables you to get.
Well, you can't, Frank, it's very hard or difficult to measure a spike.
I know, but this one is averaging. So it measures amp hours, watt hours, whatever you want. And
I hear it
doesn't,
pop, so,
it doesn't care what waveform it is.
well,
We have all the sharp grad students.
I have my theory on that one, Frank, we'll go into it one time.
Okay.
This is the best we can do with that.
You can't measure,
But that's the point.
You can't measure. a current that's zero. It won't integrate.
Yeah.
Yeah, you
But
can't.
but the current is not.
Well, the current is, the current coming from this machine, yeah, monitor, right? Now, it's not gonna load the batteries, is it? Because it's gonna take away from you.
No. It's just the measurement mode.
Okay.
So you have a
No load.
voltage, you have a voltage path, and you have a current path. glass on this one, like a power meter. It's nothing else but a power meter. It has two parts. And no matter what you measure, it does not change the current.
No, there's a way around it.
Well, the real effects of current in the battery.
Yeah.
There's two places where the real effects of current. And that process in the motor generator that we're using, it's also what is causing the current in the battery. We are not, I would rather not go into how we're charging the batteries, but we're not using the normal charging process.
Yeah, it's the, yeah,
If we did,
Then you would see
pay
it
for every
current.
bit of that.
yeah.
But you should see something. You should see a snap, Frank. Well, the scope will see it.
So of course, it's not showing me, giving me any.
Right, because
any
what's
answer.
charging that battery, what's coming out of this machine, that meter can't react to.
Well, what you have is really, in the normal closed current loops, we normally have electrons all the way through the loop.
Yes,
The battery is one of those beautiful places where you don't have that.
yeah.
Essentially, between the plates inside the battery, we
The
have
ions.
ion plates. And the electrons only go to the outsides of the plates, and from there, the external circuit back and forth.
Yes.
And the real secret is that the mass per charge, mass per unit charge, electron is very small, very small mass.
Yes.
Big old ions are much heavier. So we can hit them real hard with electrons, deliver that potential voltage to the ions. Well, the ions have started moving in, but they got the potential. We only have to pay if they're moving, you see. We're paying to get it. So we can save what we have to pay as normal current dissipation by just delivering pure voltage from that to them, rather than pure power. And the electrons are so small, they pile up and make the potential much higher on the ions. So when the ions finally get moving, they have more potential on them than they normally would have, and we didn't pay for that.
Yeah.
We didn't have to pay for all that much potential moving ions. We just put the potential on before they moved, so we had no dissipation to speak of. There's a little bit. And so then we're off there with that pulse with the electrons before we have to pay for it. If we stay on there with electrons, we'll pay for every bit of that.
But still, you should be able to detect some current.
Well, we
Average.
could, if we,
Average.
if
No,
we go
Well,
get
there's a
it.
reason, let me put it this way.
We can do that if you
The reason why
want,
we
Frank.
Because we have another current, but you gotta go all the way over to particle physics to find it. It isn't in the electrodynamics book. It's just beginning to be. There's a few papers right out there at the forefront where they're beginning to look at that and saying, you know, we have this. But so far, nobody has cranked it into the normal electrodynamics book. But it's there, and it's over in this good physics. So we have another current, which effectively gives you a sum zero current. We almost sum out the current that we had to pay for. So the other current reacts with it and keeps us from having to pay for it. If we didn't do something like that, so we get some energy in that we don't have to pay for it. If we didn't get some extra energy, we couldn't possibly ever go, you know, we couldn't get more energy in those batteries. We forcibly paid for it, wouldn't we? So the whole thing is, see, work is when you forcibly change the form of energy. Just to move energy doesn't cost you any work. It's only when you change the form of
I
it.
hate to give up. And
So-
if you guys will acknowledge that if I do this, I'm gonna give up a little bit of my charge. But you can see it.
I'm just observing. Whatever you do.
Well, no, I mean, I wanna stay conformed to your test, right?
Okay.
But you are interested in what is going to the battery,
Yes.
okay?
So we
So
know
that's
the
what I'm
resistance.
saying, if you guys will
Yeah.
acknowledge that I'm gonna give up.
Yes.
Be careful, because that's, I don't know, go ahead and do what you want to do, but just be careful, don't give up too much.
Well, I'm only gonna give it up for a second.
That's good, that's good. Then.
Okay, so you will put a
We're
resistance.
gonna stop it, okay? So I'm gonna stop the motor.
Okay, at
Okay,
1 hour,
let
17
me-
minutes.
Let me take the,
So Frank can see what it is.
okay, So, whenever you stop, tell me.
I'm gonna stop now.
Okay, 1 hour.
1755.
Okay. Now, this line here,
Is our current,
this is your current right here to the battery,
yes,
this green line,
Yes.
right?
yes,
So you break this line
yes.
right here,
Put a,
put this resistor in here,
yeah.
0.05.
Okay,
Take the tech scope or your scope,
yeah.
whatever scope you want to use.
Let's use that one. Seems to be working better than mine.
Okay, take this. I'm gonna disconnect these right now. So I'm gonna put the wire back. Okay,
Alright, so
this is your scope.
this one out.
Your scope is gonna stay on the battery.
Okay.
You'll see current now. There is nothing in that resistor that's got heavier M per cube.
Right.
No.
So the electrons will move as soon as you hit it. You'll
Yeah.
see the current now that we're stopping in the other process.
Yeah, I wanna make sure you see it all, right?
Yeah.
So, you know, there's no doubt. Now you take the scope, right? And since the scope is floating out there,
Yeah.
you go across the resistor. Now, any little change that comes through here,
Yes. So what we are seeing
Well,
now
we're gonna
is
go to
the
scope.
voltage of the capacitor.
you're gonna see every time that dumps a charge that this meter won't see.
But what we are measuring.
Well, you're seeing the voltage on
On
the
the
capacitor right now, so you wanna go to the scope,
Okay,
okay?
fine. And
Time is
So
1:19:57.
we're starting.
About 2
Okay.
minutes.
So now, that is what's coming across that resistor.
yeah,
See it?
yes. That's the
Now,
current.
let's take
Yeah.
the scope
See it.
and go to the menu where DC coupled,
Yeah.
okay? So we're gonna go up, right?
Yeah.
Bring this out. Okay, now, take the voltmeter off the capacitor, right? And we should be able to go across this resistor because then the two are in series. We're gonna get across the resistor. I'm gonna get across it. Okay, there's your battery, right? So you know that the
5,
battery's
6
there,
volts, yeah.
okay? Now we're gonna go up. Get rid of this. That's what's across the resistor right there.
Let's see voltage drop across the
Yeah,
resistor.
yes. And that's what you're looking for with this. Um, So what you're seeing push this battery up is millivolts.
Yeah.
Okay, let me explain that before you go, because that's a very important point.
Okay, wait, Tom, go.
You don't let it get on anything. When we have this resistor across here, we have a loop that's all electrons, standard. So our electron relaxation time, electron gas in the water, is very small. It's so small it approaches zero. It's 10 to the minus 16 or something. You're aware of it.
Yes.
So we don't even have to take that into account at this kind of thing unless we're at the most god-awful frequency you ever heard of. So we don't have any kind of pile up to increase the electron density and therefore the voltage. But when we have an ion delay, the relaxation time is quite longer than the electrons for that ions to actually start moving. The electrons pile up and that increases your charge density, which is a direct increase of voltage. So the actual voltage we get inside the battery is quite a bit greater than what you can measure here on the, across the resistor. It's strictly because of that greatly increased relaxation time and the ion movement.
Yeah.
Yeah, see, it's up there, Frank. See? You're coming across.
Yeah.
I'm trying to get it down to where you can see. See, the peak's all over the place. This is why this meter's
Yes.
having a hard time.
Right, because it's too short.
So, basically, now if we go to the scope, this is what you would see.
And this is in
It would be,
what is it, time base, 2 milliseconds?
it's 6.92 millivolts
Okay, that's a peak.
per division.
And our time base is
Yeah,
100
time base.
2 milliseconds.
100, well, it's 100 millivolts per division.
Yeah.
Its time base is 692,
Time base is
Yeah.
2 milliseconds.
2 milliseconds.
Okay. So our
So you should go to 1 second, right?
Our pulse is, no, that's fine. So our pulse is at 50%, round about, what?
Well,
By
it's
5,
100,
400,
200, 300, 400, 500.
400
Actually, it's above it, see? Oh, you want the average, right?
Yes,
Okay.
across the pulse, so round about 400 microseconds.
Yeah.
Right.
Yeah.
400 microseconds.
Well, you know how we can check that? Just go out one.
Yeah.
Okay, that's 1 millisecond, see? So it's
It's 1 millisecond.
1,
per division.
2, yeah,
400.
Yeah.
400 microseconds.
400 microseconds.
So
It's up
the
there,
pulse
folks.
is,
It's quick.
Oh, yeah. It has to be quick, because what we want to do, we want to get that voltage on those ions before they start
Goes the other way.
moving very much, because that costs us if we're still
Yeah.
connected to them and they're moving. But if we can get the voltage on them before they relax, to start moving, and then get away from them as they start moving,
Yeah.
it doesn't cost us anything
Yeah.
just to do that.
So can I go back to my battery now, Frank?
please, yes.
I'll go back to where we were. What I'm gonna do is I'm gonna stop the motor.
Yes.
So stop.
Let me take the time here, yes.
125.44.
Stopped. This is your normal input to us. Okay,
So we connect.
take, I'm gonna reconnect it back up where it
Yeah.
was so you can see everything again.
So how do we account for the losses in those coils?
I'm
The current lock coil of the meter.
Oh,
We have a pass.
yeah. See, well, you'd have to have the exact amount of ohms that's going through here,
Yes,
and that can be measured.
yes. Yeah, let's later measure it, yes.
Okay, go ahead, you want to measure now? Yeah, while we're doing this, I mean, we're not losing anything, nothing's draining anything.
Because we are giving up already by connecting this
Yeah.
meter.
Right.
So let me check the pass. The ohms.
Kind of interesting, isn't it, Tom?
That's good, that's good. At least Frank knows about relaxation time.
Yeah.
see? That's good.
I don't think there's any loss, Frank, is there?
It doesn't give me. Just double check maybe.
Well, see, we don't see any ohms, right? We should have a dead zero.
We don't have it. That's why.
I'm wondering if we were ever even charging the battery.
Oops. Sorry, it's not connected.
Okay.
Okay, so going as low as possible.
4/10 of an ohm.
Could be around 4/10 of an ohm.
Can you go lower?
That's through your resistor, right?
Don't,
That's through the
Yeah.
power monitor.
Okay, through the power line.
Yeah.
That's
yes,
okay.
that's the coil of the,
Yeah.
Okay? So we're okay.
Yeah, but we have to account for those losses somehow.
Okay, all right,
So let's say 0.4 ohms.
okay.
All right.
So now
let's
we gonna
reconnect.
connect back, right?
Yes.
So you know which one goes where. This one goes here.
This is the minus side.
No, this is the plus side.
Okay, then this goes here. No. We are coming from here.
Okay,
This is our plus.
yeah. And that becomes minus, really, technically. I like those clips, Frank.
Yeah.
They're real finger snappers.
Real alligators.
Okay, so we going back?
Yes, please.
We're starting now?
Okay,
Yes.
timer goes at 1:28:47.
You're stopping the start, well, 10 minutes and 45 seconds. So, would you have?
No, we,
Together, I must
Pause.
have accumulated time.
Okay, that's good. The motor was off for 10 minutes and 45 seconds. That
So
means,
I
I
have
thought the first time was off for 2. Was it off for 8?
Okay, now. You asked a question. I'll give you the answer. You wanted to know how much the coil is burning, right?
burning in
Yeah, you wanted to know how much you're losing in the coil.
actually in this coil.
Oh, that coil.
Yes. In my current path of the wattmeter.
Okay, let's go back forward a little bit. I can go back. You can go back to the scope and see the waveform.
Let's check across the current loop.
Okay,
here.
okay, good.
Across here
Fine.
with the meter.
With the meter or the scope?
With the
The
scope.
meter?
With the scope.
Okay.
And see what
So
voltage
either
drop,
way, it should be okay.
what voltage drop we are going to see.
right?
Yeah.
I got a cut right here.
That's a lot higher, Frank, so they're losing a lot more across the meter. See that? So let's go down. We're almost
Then
lose.
probably the entire voltage. Should show the entire voltage.
Well,
That's not.
it's saying there's 500 millivolts per division.
2 watts is the same, but
Well, that, we don't have that hooked up.
it should show the,
There's one more lead.
so,
Okay, so go across the current loop, right?
yes.
This becomes technical as hell, don't it?
Yeah, we have to quantify as much as we can, as much as we are able to see.
Yep.
Good.
I kind of agree. Can't argue with you, Frank. Okay. Now we want DC, right? Mhm.
So it goes up to
That's-
for
Yeah.
6 point whatever milliwatts.
Yeah.
Milliwatts and
It's 0.4 ohms, right?
yes, we have 0.4 ohms. Right.
Okay, so 0.4 ohms times
Uh,
6.5 million max.
so we
Yeah, 6.3, see?
right. What do we want? We want to have the
You want to know what current's
current.
being wasted
Exactly,
here.
yes. So I equals V divided by R.
Right.
So we have 6.2 milliwatts. Or 6.5.
Max, yeah.
6.5
6.2.
milliwatts. So this is roughly 15
I knew it was coming. It's hard to do.
What?
I knew it was coming, it was too hard to do. See, you know, you can see when this battery moves. Because all of a sudden it'll go and jump itself way up, Tom, and then that ion will relax and come back down. So actually, you know, it's building diamonds.
See, actually what happens when those electrons pile up, initially that's the charge. So
I'm gonna-
they're going in,
Gentlemen,
come back.
I'm gonna take a timeout and change tapes.
Okay.
Stopping tape. Okay, we're
readings,
rolling again.
and
Has
we
anything
have an
changed?
average current of around 15.5 milliamps
Right,
flowing through.
That we can
or
measure.
Charging is,
that we can measure.
that we can measure as an electron.
And we
Current,
should be
yes.
able to verify that by doing this. By taking the voltmeter
Yeah.
and going across these two brushes, right? Because then you've got the battery voltage minus that voltage,
Uh,
minus the capacitor voltage,
okay, yes.
right? So it's gonna be, you can see that the battery comes down to about, every once in a while you see it'll come down to 13, see?
No, 8 actually.
Yeah. So you have 12.5 minus,
12.5 minus
yeah, about 31 volts.
31 watts. So you have 31 watts
Yeah.
minus 12.5.
Right.
That's your,
That's what's above the battery.
above the battery voltage itself, which is
Right.
what,
Now,
12.5?
right, now you take what's left, right?
Okay,
Take,
that's 28, 18.5.
okay, times the current.
18.5
Times the current will give you the watts.
times 15.5
Only thing, you gotta be extremely careful when measuring the distance, the difference
Yeah.
between a circuit with hysteresis
And without,
or the ions in the circuit. When
And
you're
we'll look
measuring
at that
something
phase
with
in a
ions
minute.
Not in it, you don't have the hysteresis.
286
So it's quite a difference.
0.7 milliwatts.
right?
Milliwatts.
Yes.
So what does it tell us?
Well,
About-
we're above the battery,
Yeah,
all right? It's what it's telling us.
okay, that's basically the force
Yeah, the force that's pushing,
pushes electrons.
yeah,
Electrons only, huh?
that's what's pushing.
The electron.
Yeah, the electron push.
Yeah.
So we know that now. Now, you wanted to know,
So that's the potential difference which actually generates a current.
yes,
The
the
charging current.
yes, the potential difference, right,
Yeah.
generates the charging current in the battery.
Mhm.
Because the battery always wants to
Forcing,
go.
but only the,
That's not true.
No, what I mean is,
No, that's not true.
that's correct, my
Charging
friend.
current in the battery is the potential developed upon the ions themselves,
Right, which we can't measure.
which you cannot really measure with the electron circuit only.
yeah.
You can say
We can
it's always
only-
greater than
Yeah.
what you can measure in the electron circuit. That is a true statement.
Okay, then the difference we're talking about,
The whole purpose is to produce an excess voltage on
Yeah.
an ion that you don't have to pay for.
Yeah.
If
And
you
then
can get
cut it
that
off.
and get away from it before you start paying for it, and let the ions then have to move because they got a force on them from the gradient there to the other plate.
Mhm.
If you can get that force made for you that because of the way you broke up the circuit loop then you can get the effect. If you don't do that, you don't get the effect. In other words, voltage is energy per collecting coulomb, joules per collecting coulomb. That's what a voltage is. And if you got all these coulombs in the battery and you cause that voltage to go up, you don't have to pay for just voltage before those coulombs move. And basically, you over-potentialize the battery. That's the correct term.
Yeah,
And you do it almost for
so the
free.
battery wants to move.
But that's energy. That's real energy. That voltage is really energy per collecting
Now, you
coulomb.
wanted
that you got it
to
on.
look, Frank, at what the,
That's real energy out there when you multiply the number of coulombs of those ions.
you
in that
wanted to
battery.
look
That's
at
real
what the
energy.
motor
But you didn't have to
is
pay.
actually doing, right?
You didn't have to pay to move it in. Voltage is the movement of energy or whatever you
Boy,
want.
break that wire loose out, you saw
And a
it.
watt is the collecting end.
The watt is the dissipation of energy, or changing the form of the energy. The time rate at which that's done.
It's going to be across that coil.
In other words, so many joules per second changing form or doing work, that's what 1 watt is.
That's why we look at a light bulb and it says 100 watts, that's a dissipation. of
That's,
energy.
it's dissipating that many, a watt is 1 joule per second lost.
On the secondary side.
Used
On the
up.
primary
It's
side.
actually still around, but it's scattered.
Yes,
You
that's-
can use it.
and we'll go
The
across
energy's
the
still there,
secondary
just
side,
scattered and
okay?
change the form.
And we'll do that, we can do that with your scope,
Okay.
because you want to see those two.
You
right?
only have to pay for what you change in form and
Secondary
lose.
side would be,
If you
Now,
change
it's
it in
gonna go,
form and do not
up front,
lose it,
so-
you're always recovering it, and you can keep using that over and over until you do lose it.
Because the energy never, it's always there. It's
Energy
just
cannot be
quantity.
created, cannot be destroyed.
Yes.
It
and
is
now
only
we're going to go
changing
across
form.
the secondary side, right?
Where you can't recover it.
Okay.
So always you want to do, think of
Okay.
2 things in your head, and that is moving the energy, changing its form, and if you're not ready to
John,
use it when you change it.
Just a little bit. You can stand in there.
No, Frank wants to know what's between the primary and the secondary.
Otherwise, that's the inefficiency of the system.
Right.
Here's the, Tom, here's the secondary versus the primary. That's the primary
Yeah,
in the transformer.
yeah.
This is the secondary.
Okay.
It's up there. It's really up there, isn't it, Frank?
Should be. We got to get, we have to have it up there to, you know, to get, basically, we have to be over potentializing those ions
Yeah,
before they get to moving very much and costing us.
yeah.
If we can do that, and then just about the time they're starting to move pretty good, we offer there, you don't pay for that. They have to drain off that energy they got collected on. They have to move and do that. They dissipate that energy.
That's
move
not
over.
high enough, Frank?
Secondary.
That's good.
So what does the secondary have there, Frank? Can you see it? Hard to see a liquid.
It's a good, if you tilt it up just a hair, your meter up just a hair in more angle, I'll get less out of it. There we go, perfect. Thank you. Now we see it beautifully. That's the secondary. 11 meters. The one guy has 3. Another one has.
It's different, isn't it, Frank? Well, see, notice the primary as opposed to, see, the secondary? See how these lines are in phase? There's no phase difference. Thanks to Sparky.
Yeah.
He's really
The commutator is not perfect.
right.
Well,
Always
the phase is missing from what you would expect with a normal inductor because he's actually using the magnetic vector potential, bypassing the B field.
Yeah, 'cause so it looks the same as that.
So
right
if
there.
you lose the swirl, if you bypass the swirl, just use an uncurled A potential. It comes out, the alternation makes an E field. DADT is an E. And so
See here?
actually it's an E
Look,
field
look.
interaction with the electrons in the wire. It
Actually, if
catches
you
it.
slow this way
That's in
down,
phase.
Yeah.
You don't see
you
that.
got the
It's
same thing
reaches.
here.
Yeah.
If you start to slow this way down.
Yeah,
See, you've
this
got,
is-
it takes these damn things forever.
Yeah, so this is dependent on your...
RPM, right.
RPM,
If you,
yeah,
if you change RPM, see,
Yeah. it will change.
it will change over here too.
Yes.
See? It might go higher. As this motor works the load, right? The current goes downward. So that's your primary. Right, now here's the base circuit. It's triggering it, right? It's clamped. And it should be opposite. Stand trigger level up here. Look, right, it's opposite.
Yeah.
It would have to be opposite. We're not triggering on the magnetic field, it has to do the opposite. So that's in the base, that's right on the, right out of the transformer to
Right,
the
right.
front of the resistor. It's kind of hard for me, you want me to get
Okay.
behind it?
So
I'll
on
get
the,
behind it and you'll see the clamp. Okay? See, you'll see the clamp. It's gonna clamp at 6/10.
Yes. right,
There it is.
yeah. Because of this diode,
Yes. That's gonna protect the junction.
yeah.